what's left? Laws of conservation in the Lagrangian formalism, right? So let's discuss just briefly, right? Because we will go much deeper in the graduate level course about these laws of conservation, deriving almost everything, justifying everything. So, if let's start with which one? Okay, let's start with, for example, x. What if your Lagrangian is not a function of x? X is a translational coordinate. Let's assume it's not a function of x. It means what? It means that x is ignorable or cyclic. X is ignorable, right, or cyclic. So in that case, you remember what happens? dl over dx is 0, right? And then the corresponding generalized momentum is conserved, right? So, and of course, generalized momentum in this case is just linear momentum in the x direction. So in this case, I can write that px, which way I wrote it, just px is equals to constant. So it leads to the conservation of linear momentum in x direction, right? So that's, again, you can see it from the Lagrange equation immediately, right? So we've done it in the past. Now let's look at this function L. It's not a function of x. So we can say that L is invariant under the x translation along the x direction, right? And so probably I will write so x. Oh no, I mean L. L is invariant. Basically, it doesn't depend. It's invariant. Invariant, which we wrote it under translation. Under translation in x direction. And again, you remember, if you know Lagrangian, you know everything about the system. You can easily get its evolution, right? So you can write Lagrange equation, and you can see the life of the system. So let's assume that this is x-axis, right? So x is missing, so this is the x. So if you let's say this is x1, and you position your system over here. Let's assume that this is your system, and its Lagrangian is L. So if you let your system live at this point with a certain initial condition, so you put it here, release it, and it started living its life. Okay, so there will be some life. Now, if you take the same system with the same initial conditions and position it here, so of course Lagrangian will be the same because Lagrangian does not depend on x. L is invariant under the translation in the x direction. And again, since L is the same, so the life of this system at this point will be exactly the same as here. If you again leave it, let it live, so the evolution of the system here and here will be exactly the same. You wouldn't be able to see the difference. So in this case, we can say that this space is homogeneous in the x direction. So when you see something like this, when translation of the system in a certain direction is not going to change the life of the system, so we can say that the space in the x direction is homogeneous. Okay? So now let me write it. So which way I wrote? So life. Okay, let me do it like this. So life of the system is the same. So we can say that space is homogeneous. So the space is homogeneous. Space is homogeneous. Okay, running out of space. All right. Okay, let me write it then. Homogeneous. In the x direction. in the x direction. Okay, so now let me underline. So from one side, the space is homogeneous because of that. From the other side, we're getting that linear momentum in that direction is conserved. So now we can connect this with that, and we can say that conservation of linear momentum follows from homogeneity of space in that direction. Right. Sort of, this is kind of a semi-conceptual explanation, right? And of course, in a graduate level, we will go deeper. We will deeper. Okay, so now let me write this conclusion. All right, so conservation of linear momentum comes from homogeneity of space. So now, right, which way I wrote? Okay, conservation of linear momentum. Conservation of a linear momentum follows from homogeneity of space. Homogeneity. Oops. Oh no, it's right. Homogeneity of space. Okay, let me frame it, this conclusion, right? And example, what, a few classes ago, okay, couple of classes ago, we looked at the example. You remember that wedge with a block on top. It doesn't matter if we would let it live, if we let it evolve at this point, or if we displace it and let it live its life over there, the life will be exactly the same. The behavior of the system will be exactly the same. Because in this case, and of course, we saw that linear momentum in the x direction was conserved. So it's an example of that. But of course, if you grab your system and move in the vertical direction, of course, the conditions will be different. Potential energy will be different, right? As a result, the system will behave in a different way, right? So that's why in this case, space is not homogeneous, but in this direction, space is homogeneous, and it led, okay, back then, it led to the conservation of linear momentum. So first, then in a similar way, okay, maybe I can fit more over here. So now, what if Lagrangian is not a function of angle? So this is a translational coordinate, but what if it's an angle? So now if L is not a function of phi, for example, so phi is cyclic or ignorable. So in this case, of course, we know from Lagrange equation that this fact leads to conservation of generalized momentum. But of course, in this case, it's a conservation of angular momentum, right? So in this case, L, Z equals constant. Again, you see, whenever I write Lagrangian, I use this wavy L. But whenever I want to show angular momentum, I use kind of straight L. Right? So conservation of angular momentum. Conservation of angular momentum. Okay, so that's from one side, right? And then since now function L is not a function of phi, so we can say that L is invariant upon what? Upon a rotation of the system by in the phi direction. But of course, you're supposed to sort of grab the system as a whole, right, and move it. Sort of, if you let it leave your system at this angle, phi 1, so there will be some life, right? Because Lagrangian, because of that Lagrangian. But if you sort of like freeze the system to preserve initial conditions, rotate it, and unfreeze it at this angle phi, So the life of the system will be exactly the same because Lagrangian will be exactly the same. It doesn't depend on phi. So if system behaves in this way upon this rotation, so that space is isotropic. That space is isotropic. Okay, so yeah, so the space is isotropic. That will be from one side. Okay, I will write it in a second. But from the other side, it leads to the conservation of angular momentum. So we will be able to connect these two sides, and we will be able to say that conservation of angular momentum follows from isotropy of space. Right. So you see, this loss of conservation are the consequences of properties of space. Right. Okay. So now let me write this is so L is invariant under rotation. So L is invariant under rotation. Right. Okay, so maybe I will draw something. So let's say this is the system at angle phi 1. Oops. Phi 1, and then if you turn it, and let's say system will be here, of course it will be exactly the same Lagrangian. So, and this is at the angle phi 2. So you turn it by delta phi. Right. So life of the system over here at this angle and life of the system at this angle will be exactly the same. Right. So in this case, space is isotropic. All right, again, so in this case, the space is isotropic. Right. So now, if we connect this conservation of angular momentum and isotropy of space, so we can say that conservation of angular momentum follows from isotropy of space. All right, so I can write it here. So we can write so conservation of angular momentum follows from the isotropy of space, from the isotropy of space. Okay, so now I can frame this as well. Right. And the last piece, conservation of energy. This is more difficult to justify, so I will just write it, but we will prove it in the graduate level course. Right? We usually prove it in the graduate level course. Conservation of energy. Conservation of energy, it's a consequence of homogeneity in time. Okay, and then we will prove it and show in a graduate level. But now I will just write it down. So now the new bullet. So that was the first one, now the second, and now the last bullet. So what if Lagrangian is not a function of time? So time is not explicitly present in the Lagrangian. In that case, it leads to the conservation of energy, mechanical energy, and again, it follows from the homogeneity of time. So now let me write it down. So it leads to the conservation of mechanical energy. So if you see the Lagrangian and there is no explicit time dependence, okay, you can say that energy is conserved. You can say that the system basically is not driven, but if you have a system which is spinning at constant angular velocity, it means that there is some driving force, right? So in that case, Lagrangian will have time dependence. Right, and so conservation of mechanical energy, as I said, conservation of mechanical energy follows from homogeneity, follows from homogeneity of time. Okay. So now let me frame it. But again, the last piece we're not going to justify, neither justify nor prove. So I usually state it. And again, the proof will be in the graduate level course. So all laws of conservation are the consequences of properties of space in time. Sounds very lofty. Okay, so at this point, we can say enough of the Lagrangian formalism. Right. So now, chapter 8, two-body problem, central forces and two-body problem. You know what? Probably I will start erasing, because now I will need plenty of whiteboard, and so it's better if I start moving from this point. Right, but before we go into chapter 8, two-body problem, let's introduce the central forces, which is done in this book in chapter 4. But I usually skip it in chapter 4 and just move it to this point of the course. So first, let's introduce central forces, and then actually we will start discussing two-body problem. Right, so now central forces. Again, this comes from chapter 4. Okay, maybe I should write so. Chapter 4, it's just before going into two-body problem. So let's assume that we have some force center. I don't know, maybe mass, or maybe a charge. Force center. And of course, you can introduce coordinate system, right? So let me write it's a force center. And let's say you are interested in the force created by this force center at that point, which is at defined by the radius vector r. Of course, there will be some force F, which is a function of r. Right. So if force F can be written as absolute value of the force at that point times unit vector in the r direction, basically it means that the force, if a force acts along the r direction, so it means that that force is called a central force, right? So this force is a central force. So direction of the force is along r hat or in the opposite direction to r hat. Examples, of course, we all know. So F, electric force, it will be what? K, Q1, which are Q smaller? I think, yeah, I use Q small and Q capital. Q over r squared r hat, or F, gravitational, it will be a minus G, m small, m capital, over r squared r hat. Here minus, because all the time it's a force of attraction. This, I didn't put any plus or minus because it depends on the charges, sign of the charges, Q small and Q capital, right? So it can be force of attraction or it can be force of repulsion, but both of them central forces, example of central forces. Of course, you can come up with more complicated examples, but these are the most typical. Then, another thing. spherically symmetric force. Okay, maybe I will write. So, which way I wrote it? So, a central force is spherically symmetric. So if, for example, this is the force center, right, and you're interested in the force at this point, all right, so the value of the force at this point, or at this point, at the same distance from the force center, or at this point, or that point, this point, at any point on the circle, if the force, magnitude of the force is exactly the same, so we can say that this force is spherically symmetric, right? So it doesn't depend on the radius r. It depends only on the distance, absolute value of the radius r, right? So in this case, the force is spherically symmetric. Okay, so now a central force is spherically symmetric when this absolute value, f, is not a function of a vector, it's a function of an absolute value of r. So when f of r equals to f of an absolute value of r. So in this case, the force is spherically symmetric. Okay, let me frame it. And I mean underline and this underline. So then what's next? Yeah, test. So which test do we have to run in order to convince ourselves that the force is spherically symmetric? So, basically, okay, it means if you take a partial derivative of a force with respect to phi, it must be 0. So it means that this partial derivative must be 0, and of course, partial derivative of the force with respect to theta must be equal to 0. Basically, these two conditions can be used, or not can be used, are used as a test to convince that this or that central force is spherically symmetric. Right. So if partial derivative with respect to theta is 0, and with respect to phi is 0, then okay, so let me write. So this is the test for spherical symmetry. Spherical symmetry of the force. All right, so now we need to prove one interesting feature, and then we will actually start moving to two-body problem. So the feature is this. So if you have a central force, and that central force is conservative, then automatically that force is spherically symmetric. We will be using this fact from time to time. Actually, not much time left, only 2 weeks, right? But anyway, so again, if, maybe I will write. So now, interesting feature. Let me write. I will put a new bullet. So, interesting feature. Or you can call it remarkable. That's what it's written in my notes, but enough of a remarkable feature, so I decided to call it interesting. All right, so if force F is, which way? Central and conservative, examples, both of these forces, central and both of them conservative, of course, they're spherically symmetric. We know that, right? So, and that's, if F is central and conservative, then it's spherically symmetric. Spherically symmetric. Oops. created a mess. Symmetric. Right. Okay, so let me frame it quickly. Right. And let's prove it. Proof, it's very short, so let me do it. Again, it's done in chapter 4. But I move it here because it's more relevant in chapter 8. Right, so let's prove it. Proof. So F, our force, F as a function of R, right? Of course, first we can use the fact that it's central. Okay, let me first, because you see we have two conditions, force central and conservative. So first let's use the fact that it's central. So at this point, I use the fact that it's central. And I can write it in this way. So F as a function of R times R hat. Now, second over here, we're going to use the fact that this force is conservative. And of course, if it's conservative, we can write it as a negative gradient of the potential energy. So minus gradient of U, right? Okay, as a function of R. And of course, now let's write down explicitly gradient in spherical coordinates, because we use spherical, obvious. The choice of the coordinates are obvious. All right, so it will be minus R hat, partial derivative of U with respect to R, then minus theta hat over R, partial derivative of U with respect to theta, and the last term minus phi hat over R sine theta and partial derivative of U with respect to phi. So explicit form, okay, gradient written explicitly. Okay, let me check if I didn't make any mistakes. No, it's good. Now, so we know that the force is conservative, and it should have only term in the radial direction. So it means that this term must be equal to 0, and this term must be equal to 0 for any R, for any theta, for any phi. So it can be true only when this derivative, du over d theta, and this derivative, du over d phi, are 0. Right? Okay. So it means that this must be 0, and this must be 0, again, since it's a central force. Since F is central. So these terms must not be there. We must have only this term. So it means that du over d theta, so it means du over d theta equals to du over d phi equals to 0. And that's our basically test to convince ourselves that function, in this case not f, function u, is spherically symmetric. So according to this, u is spherically symmetric. So it means u is spherically symmetric. Spherically symmetric. Okay. So, but again, it's a spherical symmetry of the potential energy. Actually, we will use it in maybe 10 minutes, 10, 15 minutes. But now, we need to show that F is spherical symmetric. Okay, look. U, if you differentiate U with respect to R, you will get F, right? Yeah. And if U is spherically symmetric, then differentiation with respect to R is not going to ruin spherical symmetry. In order to do something bad or good with spherical symmetry, right, you need to do something with theta and phi. But we are differentiating with respect to R, spherically symmetric function. So it means that spherical symmetry will be still there. So the force F will be still spherically symmetric. Okay, so now let me write that conclusion. So spherical is, okay, I need to erase this. I didn't realize that it's still here. Okay. And so just, so I wrote spherical symmetry. Okay. And so then a partial derivative of u with respect to r does not ruin spherical symmetry. Right, does not ruin spherical symmetry, and that's essential part of the f, right? So this will be still spherically symmetric. So f is spherically symmetric. Spherically symmetric. Okay, so it's kind of very quick proof, and again, as I said, we will need it from time to time. Right. And even in a graduate level course, I sometimes refer to that. Okay, guys, you remember in the undergraduate level course, we proved that. Okay, so now two-body problem. Two-body problem. So now finally, chapter 8. So now, chapter 8, two-body problem. Right. So what do we have over here? Two masses, right? M1, M2, are isolated. So they move under the influence of each other. So this object exerts force on this one, and this one exerts force on that one, and then they move somehow. Again, no external forces. The system is this. External forces, there are no any other objects in the universe. Right? So isolated, two isolated masses. Okay, so let me write that down. So we have two isolated bodies moving under the influence of mutual central forces. And we're going to make two assumptions, that those forces acting between two objects are central and conservative. So I will write it down. But first, let me write in general that we have so two isolated objects. Actually, strictly speaking, it's point masses, right? Moving under the influence of mutual central forces. Moving under the influence of a mutual central force. Mutual central force. Okay. Examples, of course, you all understand the sun and, the Earth and the Moon two-body problem. Of course, if you neglect influences of other objects, right? Of course, sometimes you cannot do that. Binary stars, right? So hydrogen atom, electron, and nucleus inside, right? So there are plenty of examples like this. Of course, under certain level of approximation, these can be used to describe systems like what I just mentioned. Okay, so now let's set up the problem. So let's assume that we have two bodies, right? So let's say the first one is here. The second one, let's assume here. So this is what? M2, right? Yeah. This is M2. This is M1. We're going to use Lagrangian formalism to describe this problem. So it means that reference frame must be inertial. right? So let me position it here. So this is the origin, O, and again, I will emphasize it's a inertial RF. So position of this object is defined by the radius vector R1. And position of this, of course, is defined by the radius vector R2. All right. Then, of course, forces. Let me draw this dashed line. So force on the first object which comes from the second will be this. So it will be F on 1 from 2, F1, 2. Force on 1 from 2. And of course, this one, experience force F2, 1. So it acts on 2 and comes from object 1. So about those two forces, so let's make assumptions. So F1, 2, okay, let me emphasize, it's on 1 from 2. And this F2, 1 central plus conservative. So let's make this assumption. Then, I'm just trying to make sure that I don't miss anything. Then, you remember in chapter 4, we discussed, again, we did not derive, we just discussed it. If you have a system like this, isolated system of two bodies, right, moving under the influence of each other, then in that case, we can introduce a single potential energy. Single potential energy, and this force can be derived from that potential, and this force can be derived from that potential, right? So again, which way I wrote. So from chapter 4, so we can introduce a single potential. Okay, potential energy, not potential. Single potential energy, which is U as a function of R1 and R2. Right? Again, in chapter 4, we discussed it. And these forces can be derived. So let's say from this potential F1, 2 equals minus gradient. Of course, gradient taking with respect to the coordinates of particle 1, on which object this force acts. So gradient of U. And then, of course, we can write similar for F2, 1, again, minus gradient with respect to R2 out of our single potential energy, right? So connecting chapter 4 results with these results. So, and now, after this, basically, we can write down the Lagrangian, right? We don't have any constraints, right? Again, constraints appears if you have forces of constraints. No, our forces are conservative forces. We can introduce potential energy, and they appear in the Lagrangian in the form of the potential energy. There is no point of treating them as forces of constraints. They are not. Right. Okay, so now the Lagrangian will be, so L will be, of course, T minus U equals 1 over 2 M1 R1 dot squared plus 1 over 2 M2 R2 dot squared and minus our potential energy, which we just introduced. Again, you see, because there are no constraints, so there is no point of introducing some transformation equations, right? Reduce number of coordinates, because they're all 6 coordinates describing the system are linearly independent. x1, y1, z1, x2, y2, z2, right? 6 coordinates are needed, and they're all linearly independent. So that's why we can write immediately this Lagrangian. Okay, so now before we start doing anything, let's simplify. Let's simplify it. Which part? Potential energy. Let's make some assumptions in order to simplify the expression for the potential energy. So, okay, I think I should be able to squeeze. Okay, let me frame with blue. So it's a first form of the Lagrangian. There will be several forms of this Lagrangian. We will keep massaging this Lagrangian until we will get very, very nice Lagrangian. So it's a first form. So simplify. So the goal of now, a few steps, will be simplify u, of course, which is a function of R1 and R2, right? Simplifications. So first assumption, any isolated system is translationally invariant. I think it should be obvious, more or less, right? So because there are no any external forces, so if you have a isolated system of two bodies, right? And let's say this is the reference point. It doesn't matter if you position it here or there or here, right? So potential energy should be the same. So it means what? It means that potential energy should not depend just on R1 and R2. It should depend on R1 minus R2. Because again, no external forces, it doesn't matter where this system relative to the origin is. Of course, if you don't change orientation. For now, it's a first step. So any isolated system is translationally invariant. Of course, if you don't rotate, if you just move the whole system as a frozen. Right? All right, so then we can simplify potential energy. Okay, so it's a first step, and then of course there will be the second one. Right, so any isolated system is translationally invariant. Right, so translationally invariant. So it means that instead of u as a function of R1 and R2, we can write it's a u as a function of R1 minus R2, but still a vector. So it will be u as a function of R1 minus R2. So now the second step in simplification, in an attempt to simplify potential energy. So we just said that these forces are central and conservative. Central and conservative, right? And we just saw that it will be also spherically symmetric. Spherically symmetric, right? And we saw also in the last step in this proof that spherical symmetry of the force and spherical symmetry of the potential energy follows from each other immediately, right? So again, so we made the assumption that forces are central and conservative. And according to this proof, it means that force is spherically symmetric. But again, since force and the potential energy are connected through the derivative with respect to r, so spherical symmetry of the force and spherical symmetry of the potential energy follows from each other immediately. Right, so as a result, instead of potential energy as a function of R1 of a vector R1 minus R2, we can write potential energy of an absolute value of R1 minus R2, absolute value of a relative position vector. Okay, so now let me write this. So conservative central force, conservative central force is spherically symmetric. That's why I spent 5 minutes deriving that. Is spherically symmetric. In order to use it here. And of course, U is spherically symmetric. It's getting more and more difficult to write here. also spherically symmetric, so it means that instead of u as a function of a vector, we can write u as a function of an absolute value. So u as a function of r1 and r2, we can write as u as a function of absolute value of r1 minus r2. And this is the relative position vector. Let's show it on the picture. This is the relative position vector. Okay, let me draw it here. So this will be, all right, so r equals to r1 minus r2. Right, okay, it's time to start erasing this. Yeah, I don't need it all. So now let's introduce this relative position vector. So relative position vector. So we introduce it as r equals to r1 minus r2. So as a result, our potential energy, U as a function of r1 and r2 can be written as U as a function of just r. It's a significant simplification, right? So now, the second form of the Lagrangian. So let's just rewrite it and see what is good and not good about that Lagrangian. So now the second form of the Lagrangian, it will be again 1 over 2 m1 r1 dot squared plus 1 over 2 m2. So m2 r2 dot squared and minus u as a function of r again. So let me frame it slightly. Okay, great. It's easier, but what is still not good about the Lagrangian? Again, nothing is wrong, but maybe we can make it better, right? So the major trouble about this Lagrangian, look, this term depends on R1. This term depends on R2 only. But this term depends on both R1 and R2. Of course, inside of R, it's a R1 and R2 absolute value of that. So effectively, this is a coupled Lagrangian. It means what? It means that, sorry, if you write down Lagrange equations, you're going to get two second-order differential equations coupled differential equations. Of course, solving them is not going to be fun, right? It's going to be problematic, right? So what if we try to decouple this Lagrangian? Maybe we can move to a different coordinates where this Lagrangian will become decoupled. Maybe there's one or two terms which depends on one coordinate. The other term or two terms depends on the second coordinate, a set of coordinates. Let's make an attempt to decouple this Lagrangian, because right now it is coupled. Otherwise, there's nothing wrong with this Lagrangian. So, okay, so this Lagrangian is coupled. This Lagrangian is coupled. And it's not good. It's not wrong, it's not bad, it's just not good. Maybe we can simplify it. So let's try to decouple it. Try to decouple it. Okay, so now that's the goal for the next maybe 10 or 15, okay, 10 minutes maybe, right? In an attempt to decouple. So let me check if I mentioned everything. Yeah. Good. Okay, so now we will need to write sort of transformation equations, but now again we we're not trying to reduce number of coordinates. We cannot do that because all these coordinates right now, which we're using, are linearly independent. We can just change from that set of coordinates, 6 coordinates. We can move maybe to a different set of coordinates, but of course there will be still 6 of them because we don't have constraints. Right? But still nothing wrong with trying different coordinates. Right? So, okay, use different coordinates. So let's just move from R1 and R2 to position of center of mass plus relative position vector. R and R small. And of course, R it's a center of mass. R, center of mass position. And of course, R small I already introduced. It's a relative position vector. Okay? And transformation equations. Of course, we can easily write. So transformation equations. So first, in order to move from, okay, so let me write first. It will be M1 R1 plus M2 R2 divided by the total mass of the system. So it allows us to move from R capital R small to R1 and R2. Right. And of course, the second transformation equation is that. So R equals R1 minus R2. But we need to move in the opposite direction, in the reverse direction. We need to move from R1 and R2 to R small and R capital. So let's invert these equations. It can be easily done, simple algebra, right? Invert them. Of course, you will end up, okay, I'm not going to do that algebra. I did it a couple of times and then decided, no, it's not worth of that. No, not worth of doing it. So R1 equals to R capital plus M2 R. Okay. No, yeah, it's good. It's good. Yeah, it's correct. Why I started doubting myself. Right. So divided by M capital R small. Right. First, and of course, similar for R2, we can write position of the center of mass minus M1 divided by the total mass in R small relative position vector. Okay, so let me frame them because these guys, that's what we need. So we need to plug them in the Lagrangian, differentiate that with respect to time, square, then differentiate this with respect to time, squared. Here, coupling term will be positive when you square it. Right? Here, coupling term is going to be negative. So this positive coupling term with that negative coupling term are going to cancel each other. And that's where, that's the point where mathematically Lagrangian becomes decoupled. Of course, I'm not going to plug and square it. No, no, no. I've done it once or twice, and then I decided, no, it's I shouldn't be doing that. So now let me write. So this is 1. Let's say 1. So now put them in 1, and as a result, after some algebra, you will end up with this Lagrangian. So Lagrangian equals 1 over 2 m capital R dot squared plus 1 over 2 mu reduced mass. In a second, I will write what reduced mass is, right? But I'm sure that you're familiar with reduced mass at this point, times R dot squared, relative position vector, and minus potential energy. Yeah, potential energy is not going to change. Right? So minus U as a function of R. Okay, so that's the new form of the Lagrangian. It's the third form. And of course, now let me write down the reduced mass, mu. Right, so reduced mass, mu. Okay, no, let me write it in a different way. So 1 over mu equals to 1 over m1 plus 1 over m2. And of course, you can write mu equals the product of masses divided by the sum of masses. Reduced mass. Again, it naturally follows when you go through these algebraic transformations. Right, properties of this reduced mass. First of all, reduced mass is smaller than both of the masses which creates this reduced mass. So it's smaller than m1 and smaller than m2 all the time. Then if one of the masses, which one I used, okay, let's say m1 is much larger than m2. For example, this is the sun and this is the earth. Or maybe this is the moon and this is the earth. In that case, reduced mass equals to the mass of the smallest object. Okay, not the smallest, the one which has smallest mass. Right, so in this case, the reduced mass is approximately equal to m2. Right. Okay, just since we introduced it, it's worth of mentioning some properties of this reduced mass. Okay, now let's look at this Lagrangian. Now, first of all, it's decoupled. That's what we wanted to get. So this term depends only on r capital, position of the center of mass. Okay, velocity of the center of mass, but anyway, r dot. Then this depends on r small, and this depends on r small. So basically, this Lagrangian depends only on r small, relative position vector. That depends on r capital. So decoupled. That's what we wanted to get. Right. So let me write. Now it's decoupled. And I will put one big happy face. That's what we wanted. Right, and now also, look, effectively from the mathematical point of view, now it looks like a Lagrangian of two fake particles, or fictitious. Particle with the total mass m, position at the center of mass and moving with the velocity of the center of mass, and the fake particle with the reduced mass. So now it looks like our particles m1 and m2 kind of disappeared, and now we have two fictitious particles, and we have Lagrangian of two fictitious particles. Right. So now what's next? The next step in this line of simplifications of the Lagrangian. Look, what can you say about r capital? R capital is missing in our Lagrangian. It's not explicitly present, right? And you remember in this part which is just erased, if some coordinate is not explicitly present, of course, the corresponding linear momentum is constant, right? And so we have conservation of linear momentum, and of course, the velocities are constant. So we can say, of course, in components, so x capital is missing, so we can say that linear momentum associated with, okay, linear momentum is constant. Okay, maybe I will write. So let me first say it. So the associated linear momentum will be conserved, all right? And of course, x capital dot is constant. So it means that velocity of the center of mass in the x direction is constant. Then a similar way we can say that velocity of the center of mass in the y direction is constant, and velocity of the center of mass in the r direction, in the z direction is constant. So r dot velocity of the center of mass is constant, right? Okay, so now let me write down, and then we will try to use that fact to simplify this Lagrangian one more time. Okay, so maybe I will be able to squeeze it here. So now, next level of simplification. Okay, small bullet. So now, since R is cyclic, right? So corresponding linear momentum is conserved, and r dot equals to constant cyclic. So r dot equals to constant. So center of mass moves with a constant velocity. So the center of mass moves with a constant speed. Okay, so can we use it somehow? Let me check if I mentioned everything. Yeah. This motion of the center of mass with a constant speed, basically it's a uniform translational motion. It's a subject for physics 1 problems, right? So it's quite boring motion. There is nothing interesting about that motion of the center of mass. So most of the time people are interested in the relative position of these objects relative to each other. But the fact that the center of mass moves with a constant speed, again, uniform translational motion is physics 1. Okay, so now let's, as a result, if we are not interested in that motion, since it's kind of boring, so let's try to hide that uniform translational motion. Let's make our description blind to that uniform translational motion. Okay, so now I need to invade this part, and okay, I will keep the picture. I will just try to move around this picture because you know what, probably when I introduced the center of mass, probably I should have added on the picture, so let's say this is center of mass point, and this is our R capital. Okay, I should have added at that moment. Okay, so now, so constant speed, so it gives us a uniform translational motion. So uniform translational motion. So I will write, it's boring, right? It's boring. So let's hide it. Let's try to hide it. So let's hide that motion. So how can we do that? We can just move the origin to that point of center of mass. And since it moves with a constant speed, this new reference frame will be still inertial. Great. So we move from this point, from this reference frame, which was inertial reference frame. Now we can create a new reference frame and move to there to describe motion of this two-body system. Let's hide by moving our reference frame to the center of mass point. Okay? So as a result, this term disappears. As a result, r dot will be, of course, 0. So as a result, so r dot becomes 0. So now we will have simplified version of the Lagrangian. Right. Yeah, and also it will be still inertial. Frame to the center of mass. And, okay, let me underneath write still inertial. So that new reference frame will be still inertial because it moves with constant speed. Constant velocity, not speed. Right? Direction also the same. Okay, so as a result, right, so the next Lagrangian form of the Lagrangian will be L equals 1/2 mu r dot squared minus u as a function of r. Okay, much better, easier. Right? But again, it's still not the final form. So as a result, I will just frame it slightly with blue. So now, in order to make the final push in an attempt to simplify this Lagrangian, let's digress a little bit. Let's look at the, okay, so maybe I will put the new bullet, and yeah, I need to start erasing. Continue erasing this part. Yeah, it looks like I don't need, okay, let me stop erasing at this form of the Lagrangian. So let's digress a bit. Let's digress. So let's look at the dynamics of the angular momentum. So now we basically have a single particle in our system, right? Of course, fictitious particle, single particle with the mass of the reduced mass, right? Okay, so now let's look at dl. You see, I'm using straight L. It means that it's an angular momentum, right? So dl over dt, of course, it's a d over dt of r cross p. Right. Again, now we have single particle, fictitious. So, of course, we can differentiate this. Of course, we will get r dot cross p plus r cross p dot. So the first term, r dot, here inside m, it's a mu r dot again. So the cross product of two collinear vectors is 0. We used it in chapter 3, I think, similar. Then, of course, since our reference frame is still inertial, right, inertial, so we can write this as F. So that's the force acting on our particle, right? And of course, it's a central force. So we can write it as R cross F. And now, let me open my explanation box. Since F is central, it's a relative position vector crossed with the force along that direction. Of course, it's a 0. So it's 0. So it means the rate of change of angular momentum is 0. It means that L, angular momentum, is constant. So L is constant. And at the same time, L, by definition, it's a cross product of R and P, of course, right? So equals R cross P. And again, it's a vector constant. It means that magnitude stays the same and direction stays the same. It means that it doesn't wobble angular momentum, right? So now if I draw, okay, I need this space. So now if I draw something like this, so let's say this is my L, which I'm examining. So this is L. And it's a cross product of R and P. So let's say this is R and that is P. So the cross product of these two vectors must give us a constant vector. So pointing that way, it can be possible only when R and P lies in the same plane. Right? If they are not in the same plane, this L will start wobbling. Right? So it means from here we can say that R and P lies in the same plane. So we can create a plane out of these two vectors R and P. Right. Again, if they are not in the same plane, L is not going to be constant, direction is not going to be constant. Right? So R and P are in the same plane, or they form the same plane. Okay, so if R and P in the same plane, it means what? It means that we have two-dimensional motion. So every time we can find that plane and try to describe the motion of the system in that plane only. So we can move from three-dimensional problem to two-dimensional problem. And we can introduce polar coordinates, right? The same plane. All right, so 2D motion, and introduce the polar coordinates, or use polar coordinates. Okay, so basically the goal of this digression to say that we can introduce polar coordinates to show that this motion is two-dimensional, and we can use polar coordinates. So now let's rewrite that Lagrangian in polar coordinates. What can be easier? What can be easier than that? Right. Okay, so now finally we can write the Lagrangian equals. So now you see it's a wavy L, it's a Lagrangian now. So now single particle, two-dimensional motion, polar coordinates. It was at the very beginning of the chapter 7 we wrote that down, right? So now we can easily write it 1/2 mu r dot squared plus r squared phi dot squared. So that's first term, square of the velocity, and minus u as a function of r. So this is the final form of the Lagrangian. Okay, so now I can frame it with red. Final form of the Lagrangian. So we had like 4. 1 was erased. This is second. This is third, fourth, fifth form of the Lagrangian, right? With small simplifications every time, right? Okay, so now, okay, let me check if I mentioned everything. Yeah, so now once we got the Lagrangian, so what's next? We just need to grab Lagrange equations and start writing them for phi and for r. So let's start probably with phi. So partial derivative of L with respect to phi equals to d over dt, and partial derivative of L with respect to phi dot. Actually, I should have said at the immediately, phi is not explicitly present in the Lagrangian. It means phi is cyclic, and of course corresponding generalized momentum is conserved. And of course, since phi is an angle, so that generalized momentum is the angular momentum, right? Z direction. Right. So this is 0. Okay, let me write immediately. So phi is cyclic. Phi is cyclic. Right. So of course we can write that partial derivative of L with respect to phi dot. It will be what? Phi dot, it's here, so it will be mu r squared phi dot, right? So mu r squared phi dot, and of course, let's give it a name. Let's give a name to the constant, or let's label the constant as L. It makes sense, right? Absolute value of the angular momentum. Of course, the z component, right? And so from here, we can write that the phi dot, we will use it, L over mu r squared. Okay, I need to. Okay, why my cell phone is not telling me that the class is over? I need to check the ringtone. Okay, so at this point we will continue next class. So next we will write equation for r. Then we will digress a little bit. We will just use that equation to look at the energy approach, and then we will get back to that r equation and actually try to solve it. And we will not use that equation directly. We will just slightly adjust it, change coordinates. All right, and then we will start solving Kepler's problems, because Kepler's problems, actually Kepler's first law, elliptical orbits, we will derive using this. Okay.